Hello all, this is Dr. Srilatha working as Senior Assistant Professor in the Department of Mathematics in Vallurpalli Nageshwara VIGNANA JYOTHI Institute of Engineering and Technology. Today I am going to discuss about iterative methods. In this we are having two different methods. One is Gauss Jacobi method, another one is Gauss Seidel method. As you all are familiar with the how to solve the system of equations using matrices, that means how can we solve the number of unknowns. It may be having different categories. Suppose the system has a unique solution, how to calculate the values of number of unknowns. The system has infinite number of solutions, and another cases, in some cases we may not get the solutions. It is of inconsistent case. Now coming to in this, the Jacobi method, before entering to the system of generalized equations, are given by a11 x1 plus a12 x2 like that up to so on a1 and xn, which is equal to b1. Similarly, a21 x1 plus a22 x2 like that up to so on a2n xn, which is equal to b2. Like that we can write the generalized n linear equations in n number of unknowns. Before entering to this Gauss Jacobi method, we need to keep in mind two assumptions. The first assumption is always the system has a unique solution, and the second assumption is the coefficient matrix, that is capital A, where the coefficient matrix is nothing but, we'll be writing here the equation as the coefficients of all these equations, that is, let I write has a11, a12 like that up to so on a1n, a21, a22 like that up to so on a2n. So here we will be calling this capital A matrix as the coefficient matrix. It has no zeros in its main diagonal elements. So main diagonal elements means a11, a22, a33 like that up to so on ann. We'll be calling all these elements are non-zero diagonal elements. So whenever we need to implement this Gauss Jacobi method, we need to keep in mind these two assumptions. So after that, we need to keep in mind one more condition here. So what type of system of linear equations we need to implement this Gauss Jacobi method. So here we are having one condition. So here the sufficient condition for the convergence of the approximations, which is obtained by the Gauss Jacobi method. So always the system of equations should be diagonally dominated. So what is diagonally dominated? So if we go back to these generalized equations here, so whatever the coefficient a11 and the second equation a22 and the third equation a33 like that up to so on an, we will be calling all these are a11, a22, a33 like that up to so on an are diagonal elements. So we need to check the condition that this diagonal elements, that is the diagonally dominant, we need to keep in mind the condition is modulus of a suffix ii. It should be greater than or equal to summation j equal to 1 to n modulus of aij, for I is not equal to j. That is, the diagonal element, the modulus should be greater than or equal to remaining elements in that particular row, which implies the absolute value of the diagonal element is greater than or equal to sum of all elements of the corresponding row. So whenever we need to do this Gauss Jacobi method, first we need to check the condition whether the diagonal elements, that is whether the elements are satisfying the diagonally dominated or not. If the system of equations are diagonally dominated, then only we can move further. Otherwise, if the system of equations, we may have some equations which are not diagonally dominant. In such case, we cannot implement this method here. Right? So we need to check the condition, that is all the system of equations should be diagonally dominated. So now coming back to here, the first working procedure, we need to evaluate the number of unknowns in n system of equations. So as we all know the generalized equations, now we are going to evaluate this x1 here. So how I will be getting this x1 here? When we go back to this system of generalized equations, so I need to extract this x1 here. I need to extract this x1. So how can I write this equation here? b1 minus a12 x2 minus a13 x3 up to so on the elements whole divided by a11. So we extracted x1, similarly x2, x3 like that up to so on xn. Right? Next, now moving to next step, we need to do some initial guesses. That is how we will be starting with iterations. So we'll be taking the initial values as zeros here. So let me guess here, initial guess of the solution, substituting here. Let's suppose x naught equal to 0, that is x1 of 0 equal to 0, x2 of 0 is also equal to 0, x3 of 0 is also equal to 0, like that up to so on. The nth iteration values will be taking all the initial guesses are all equal to zeros. So substituting all these values into right hand side of the rewritten equations to obtain the first iteration values. So how we will be getting this first iteration values means we will be substituting the initial values as all are equal to zeros. So then we will be getting the first iterative values. So whenever we need to do the Gauss Jacobi method, we need to use calculators here. In the same way, the second approximation. So we will be finding the second approximation with the based on the previous first iteration values, right? So here we will be getting the second iteration values as x1 to the power 2, x2 to the power 2, like that up to so on, xn to the power 2, which is computed by substituting all the first approximation values into the right hand side of the rewritten equations. So we need to repeat this iteration procedure until, so where we need to stop here, where 2 iterations we must get all the unknowns approximately should be equal up to 3 decimal places or the 4 decimal values. So if this both are or 2 iteration values are equal, we need to stop the procedure, which gives the corresponding the number of unknowns here, right? Let me explain with one example here. So here I'm having one example. Use the Jacobi method to approximate the solution for the following system of linear equations. So here we are having 3 different equations. 5x1 minus 2x2 plus 3x3 equal to minus 1. Minus 3x1 plus 9x2 plus x3 equal to 2. 2x1 minus x2 minus 7x3 equal to 3. Continue the iterations until 2 successive approximations are identical and it is rounded to 3 significant digits. So now coming to here the solution, we need to keep in mind the first condition we need to keep in mind, that is all the system of equations should be diagonally dominated. If you check the condition here, so this is the coefficient, that is a11. So here we are having a11 equal to 5, and in here the should be dominated, should be greater than or equal to. So what is the sum of these two elements? 2 plus 3, that is 5. It may be or greater than or equal to, right? Next, coming to second equation, a22. So what is the element we are having? A22 here, 9. The modulus of 9, that is should be greater than or equal to remaining sum elements, minus 3 plus 1, minus 2, which is equal to 2. May be greater than or equal to. And next here, 7x3. So all these conditions, that is A33 should be greater than or equal to the sum of all elements here. So if this check, so if the all system of equations are diagonally dominated, then only we move on to the procedure here. So already we know how to extract the number of unknowns x1, x2, x3 from the previous given system of equations. So we will be extracting here. So we write the system of equations which is in the form x1 is equal to, since the coefficient we are having 5 here, it should be divided by 5, which is each and every element in the equation here, and we are extracting x2 from second equation and we are extracting x3 from third equation. As I discussed earlier, we need to take the first initial approximation, all elements are all equal to zeros. In order to find the first iteration values, I need to substitute here x2, x3 are all equal to zeros, then only I can get the first iteration of x1 value. Next, in for extracting x2 value for first iteration, I need to substitute x1, x3 as zeros, so that I will be getting first iteration of x2 value. Next, I need to substitute x1, x2 equal to zeros to get the first approximation of x3 value. So here, which means the first iteration values are given by just I am replacing all these elements are equal to zeros. So you can use with the help of minus 1 by 5, that is nothing but minus 0.2. So in compulsory we need to use calculators here to find the approximation values. And similarly for finding x2 here, we got it some 2 by 9, that is nothing but 0.22. And here for x3 value, just minus 3 by 7, remaining all are equal to zeros. So here minus 0.42. So these are the some first iteration values, we got it here. Next, continuing this procedure and repeating here. If we want to find out the second iteration values, we need to use all these first approximations. If we want to find out the second iteration values, we need to use the first approximation values, that is x1, x2 and x3 values here. Now moving back to here. So if we go on giving the values here, just now we calculated all these values, that is we'll be getting for first iteration values. Similarly, with the help of these values, I need to find out the second iteration values. So here second iteration values, we got it x1 as 0.146 and x2 as 0.20 and x3 as minus 0.5. And you need to check whether these two values are equal. Is it minus 0.2 equal to 0.14? No. Then we need to further proceed to the third approximation. So we need to do third approximation with the help of the second iteration values. Again, replacing here, we got some values here, x1 under third approximation. That is 0.19 and this is 0.32 and minus 0.41. And check it here whether is these two values are equal? No. Here you are having 0.14 and this is 0.19 and this is 0.20 and this is 0.32. Again, we need to move on to next iteration here. That is for fourth iteration. Again, you need to take the third iteration values. Using this, you got here x1, x2 and x3. And check it once here, again third iteration and fourth iteration. This is 0.19 and this is 0.18. No. And this is 0.32 and this is 0.33, somewhat little bit nearer to this value. And minus 0.41, this is minus 0.42. So again, we need to move on to another iteration which is based on the fourth iteration values here. And here 0.18 and this is also 0.18. We got it here somewhat. Again, here you got it 0.33, but here again 0.32. Somewhat these values are matching, but we need to move on to another approximation to find exactly. They mention in the question, we need to get after decimal places, up to 3 decimal places, we must get the same value here. Again, we are moving to sixth iteration based on the fifth iteration values. We got it here 0.186 here, and this is 0.331, and this is minus 0.423. If you check, if you compare this fifth iteration and sixth iteration values, again these are all not nearer here. Again, we are moving for seventh iteration values here. So here you got it x1 equal to 0.186 and x2 equal to 0.331 and x3 is equal to minus 0.423. If you observe, the sixth and seventh iteration values are approximately same. That is same here, not approximately. So here 0.186, here also 0.186, here 0.331, here also 0.331, and this is minus 0.423, this is also minus 0.423. So both this sixth iteration and seventh iteration values are identical or equal. So we conclude that the significant up to 3 decimal places, we got the number of unknowns, that is x1 value as 0.816 and x2 as 0.331 and x3 as minus 0.423. So in Gauss Jacobi method, you need to keep in mind the first thing is whether the system of equations are diagonally dominant or not. If this condition is satisfied, then only we move to next procedure, next step-by-step procedure here. If the system of equations are not diagonally dominated, we cannot apply this Gauss Jacobi method, right? So in this way, you can do a more number of example problems based on the working procedure what we did in the starting from first iteration to the seventh iteration values here. Compulsory, we need to use calculators to find all these values. So since they mention in the question it is absolutely up to 3 decimal places, we got the sixth and seventh iteration values are equal. So we are stopping the procedure here. So we are concluding this x1 is equal to 0.186, x2 equal to 0.331 and x3 equal to minus 0.423. Right. I hope you understand this Gauss Jacobi iterative method. Right. Thank you all. Thanks for watching. We'll see you in next video.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.